Modern astronomy reveals worlds that defy all known laws of science. Diamond planets, worlds heated to stellar temperatures, and ocean giants without a single patch of land. Today, we'll explore the most unusual planets in the universe and discover just how strange space can be. The Milky Way galaxy, this boundless cosmic island, is considered medium-sized. Within its vast expanse, scientists estimate there could be up to 100 billion planets, the overwhelming majority of which remain unexplored by humanity. To fully explore our home galaxy, much like meticulously examining every corner of a pantry in our own home, would require hundreds, if not thousands of years of painstaking work. Nevertheless, each exoplanet whose existence has been reliably confirmed by astronomers represents a unique world, possessing its own distinct features and characteristics, sometimes drastically different from the familiar realities of Earth. This astonishing uniqueness manifests in a variety of aspects. In this article, we will delve into two particularly noteworthy exoplanets that not only orbit their parent stars at extremely close distances, but are also actively evolving, transforming into something more than they originally were. Within our solar system, Mercury is the closest planet to the central star, the smallest terrestrial planet, moving rapidly at 47 kilometers per second at an average distance of 58 million kilometers from the Sun. However, this celestial object does not hold the record for speed and proximity to its parent star. That honor currently belongs to an ultra-hot Jupiter-class exoplanet designated TOI 21099b, located in a star system 855 light-years from Earth. It completes a full orbit around its star in just 16 hours. To put that into perspective, a new year on this planet occurs several times within a single Earth day. The temperature on the day side of TOI 21099b reaches approximately 3,225 degrees Celsius, almost comparable to the surface temperature of small stars. The planet is located about 2.4 million kilometers from its star. This gas giant is tidally locked, and its extreme proximity to the star makes the TOI 2109 system an ideal natural laboratory for detailed study of the process of planetary tidal disruption due to stellar gravity. Planets located in close proximity to their main sequence stars, meaning they are actively undergoing thermonuclear fusion of helium from hydrogen in their cores, exhibit truly unique and fascinating processes. According to modern scientific understanding, it is quite possible for white dwarfs to have orbiting planets, although direct evidence of this phenomenon was lacking until recently. Not long ago, in the constellation Draco, 80 light-years from our planet, a very unusual white dwarf was discovered that is regularly eclipsed by its companion. A significant portion of the light reaching Earth from the white dwarf is screened. According to the discoverers, this companion could be either a Jupiter-type planet in terms of size, or, less likely, a brown dwarf. The results of the observations were subsequently confirmed by data obtained using the Spitzer Space Infrared Telescope. The collected information reliably established the transit of the white dwarf WD 1856 Pla-534 by a non-luminous Jupiter-sized companion. This white dwarf itself is not particularly remarkable. With an effective surface temperature of 4,500 degrees Celsius, it is significantly cooler than the Sun. This fact indicates that it formed about 6 billion years ago, long before the solar system came into existence, and has since cooled considerably. Its mass is approximately half that of the Sun, and its radius is about 75 times smaller than the Sun's, meaning it is only 40% larger than Earth's. However, its uniqueness lies in the fact that it is the outer component of a visual triple star system whose inner components are red dwarfs. The white dwarf's companion, designated WD 1856b, has a semi-major axis of just 0.02 astronomical units. In other words, it is only 3 million kilometers from its star, which is 20 times less than Mercury's average orbital radius. The radius of this celestial body is just over 10 times that of Earth. Thus, compared to its star, the white dwarf WD 1856 Pl-534, this object appears to be a true giant. This circumstance explains the significant screening of the white dwarf's light that researchers observed. WD 1856b's orbital period around the white dwarf is only 34 hours. Unfortunately, the exact mass of the companion planet remains unknown at this time, as its determination requires knowledge of the radial velocity, which could not be established from the Doppler shift of spectral lines. Nevertheless, scientists were able to determine that the dynamics of brightness, change in the visible and near-infrared ranges were almost identical. From this, it follows that the exoplanet's thermal radiation flux is no more than 6% of the white dwarf's own flux. This means that such a dim body could be either a giant planet or a very low-mass brown dwarf. Subsequent analysis showed that the mass of WD 1856b should not exceed 13.8 Jupiter masses. This estimate is almost equal to, but still slightly below, the theoretical lower limit for brown dwarf masses, making their candidacy unlikely. Based on the available information, it can be reasonably concluded that this is indeed an incredibly large planet. A natural question arises. How did the companion WD 1856b, located just 3 million kilometers from the white dwarf, manage to survive the death of its star? In the process of transforming into a red giant, the parent star engulfs all celestial bodies located too close to it. For example, when the Sun completes its life cycle in approximately 5 billion years, it will engulf Mercury, Venus, and possibly even Earth. So how did planet WD 1856b manage to survive when it should have long been destroyed in its current orbit? Researchers propose two most likely hypotheses. The first suggests that the white dwarf's progenitor star expanded into a red giant before its final demise, with its outer envelope encompassing Earth's orbit. If a planet existed at a closer distance, it would have been completely immersed in this outer envelope of the giant. Surrounded by hot gas, the planet would have lost its outer layers, but its inner core could have survived. Moving through the gas plasma cloud, the planet would have experienced drag due to friction and gradually approached the star's dense core, which, after shedding its gaseous envelopes, transformed into a white dwarf. Once the star's outer layers were shed, the planet found itself again in gas-free space and settled into a stable orbit around the white dwarf. If the shedding of the red giant's envelope had been delayed, the planet would have continued its deceleration and ultimately collided with the stellar core in a grand cataclysm, preventing either cosmic object from surviving. However, this scenario seems less likely, as model simulations show that a complete shedding of the red giant's outer envelopes, with subsequent stabilization of the companion's orbit, is highly improbable due to the action of numerous dynamic mechanisms. The second scenario, supported by the same simulations, suggests that the progenitor star initially possessed several planets located in more distant orbits. After its transformation into a red giant, the stability of their orbits was disrupted. As a result, planet WD 1856b gradually shifted into a trajectory close to the white dwarf, while the others, if they existed, were ejected into open space. This realignment process could have taken approximately 1 billion years, which is consistent with the white dwarf's advanced age. It is likely that this is what happened, and at some point, the planet became larger than the star it orbits. Space is undoubtedly an amazing place, full of intriguing and mysterious phenomena and objects. Studying this unique pair is an important task for modern telescopes, which will help resolve the question of WD 1856b's origin. The Milky Way is a medium-sized galaxy that nevertheless hosts about 100 billion planets. Each of these worlds possesses its own unique properties and characteristics, sometimes drastically different from what we are accustomed to seeing in the solar system. One such unusual world could well be a rocky planet that orbits 4 stars in a single system, located at a distance of 1.5 to 2 astronomical units from the system's center. The HD 98800 system, consisting of 4 stars, is located in the constellation Crater at a distance of approximately 150 light-years from us. This world generates enormous scientific interest for studying potential phenomena occurring on such a planet. In cosmic space, there are star systems significantly more complex than our suns, including 2 or, much less frequently, even 3 stars, sometimes orbiting in very intricate paths. However, a recent discovery demonstrated that this is not the limit. A group of astronomers managed to discover a system with 4 stars. Initially, this unique system was found using the Atacama Large Millimeter, Submillimeter Array, or ALMA for short, a giant radio telescope located in Chile. The radio telescope proved to be a key instrument because the stars were surrounded by a protoplanetary disk, a ring of dust and gas from which new planets are expected to form in the future. This ring absorbs most of the light emanating from the system, which is why it remained hidden from observation for a long time. However, radio waves can penetrate through it. Using the radio telescope, researchers discovered 4 separate stars within the dust cloud. They form 2 pairs. One is directly at the center of the system, and the other orbits the first, at a distance of approximately 1 billion kilometers. Systems consisting of 4 stars are incredibly rare. The uniqueness of this cosmic body increases exponentially due to the fact that HD 98800b possesses a protoplanetary disk. Thanks to the efforts of specialists working with the Spitzer Space Telescope, astronomers were able to determine that this disk consists of 2 separate belts. The outer belt is located at an impressive distance of 5.9 astronomical units from the central part of the binary star, which almost perfectly matches the distance separating Jupiter from the Sun. Researchers hypothesize that this belt is formed from cometary bodies and asteroids. The inner belt, on the other hand, is located at a distance of 2 astronomical units from the center, comparable to the distance between the Sun and Mars, and is most likely composed of fine dust. Such a division of the protoplanetary disk into separate segments usually occurs during planet formation. However, in this particular case, it is most likely caused by a completely different reason: the powerful gravitational influence of the neighboring binary star HD 98800A. In the vast majority of star systems, the protoplanetary disk lies in the same plane relative to the central star. For example, in our solar system, all planets, as well as a significant portion of asteroids, orbit the Sun in approximately the same plane. However, this rule does not apply to the HD 98800 system. Its gas and dust disk is oriented at a right angle to the central stars. This system is the first known to possess a perpendicular disk, and such an anomaly promises many incredible discoveries. It is quite possible that if other similar older systems are found, planets moving in unusual orbits at various angles could be observed. This, in turn, could lead to the formation of new types of planets previously unknown to science, and possibly even their inhabitants. However, there is an alternative scenario. In such extreme conditions, full-fledged planets simply cannot form from the protoplanetary disk, and the planet we observe in the system may be a kind of orphan, pulled in from the bottomless depths of space. Research in this direction is actively ongoing. Space still holds countless other strange things, completely unknown to humanity. Nevertheless, it is already evident that planet formation can begin even in such polar circumbinary disks. If the process of planet formation can develop further, perhaps there is an entire population of Earth-like planets with very peculiar seasonal variations that we have yet to discover. However, despite the fact that planet formation may begin, it remains unclear to what extent they can form and maintain their stability in such a chaotic system. If planets truly existed, the view from their surface would be truly mesmerizing. A hypothetical observer would see a bright band rising from the horizon and stretching across the entire sky. From time to time, other stars would pass through it. Since the system consists of 4 stars, a total of 4 suns would be visible in the sky simultaneously. Due to all these factors, such a planet would have an extremely convoluted system of seasonal changes, completely incomparable to Earth's seasons. The exoplanet orbiting the brightest star in the system is approximately 1.35 times larger than Earth and twice as massive, receiving 5 times more solar radiation from its star. Researchers believe that the discovered object transits completely in front of its star, allowing observers on Earth to detect a barely perceptible decrease in emitted light. The incredibly powerful gravitational influence of the four stars literally tears this planet and everything on it apart. Extremely high temperatures and elevated radiation levels make this place absolutely unsuitable for the emergence of any biological life. Astronomers hope to understand whether it is possible to replenish a planet's gaseous envelope at an extremely close distance from its star due to evaporations emitted from the planet's crust. In a sense, the very presence of a planet near four stars may turn out to be a very fascinating phenomenon, despite the complete impossibility of any life existing on it. The view from the surface of an exoplanet in this system must be truly fantastic and unique. The minimum possible temperature reaches minus 273.15 degrees Celsius, which corresponds to absolute zero, where particle motion completely ceases, and the thermal energy they emit becomes zero. In this regard, a natural question arises. If there is a minimum temperature, should there also be a maximum? Logic suggests that such a point above which particles can no longer emit more thermal energy should exist. To fully comprehend this, it is necessary to consider what temperature is in general, and also to try to find the sources of the highest temperatures in the entire universe. Living organisms are endowed with the ability to sense heat and cold through their sensory organs, but to obtain objective temperature data, special measuring instruments known as thermometers are used. These devices register what is called empirical temperature, for which a specific measurement scale and number of divisions are pre-established, as, for example, in Celsius or Fahrenheit scales. In contrast, absolute temperature, expressed in Kelvin, is defined relative to a single reference point, absolute zero. It is noteworthy that if there is a minimum temperature limit, the upper limit is constrained by the Planck temperature, representing a kind of cosmic temperature, maximum. Previously, it was believed in the scientific community that the highest temperature ever artificially recreated on our planet reached 10 trillion degrees Celsius. This outstanding record was set during an experiment conducted at the Large Hadron Collider, where beams of lead ions collided with each other at speeds extremely close to the speed of light. These collisions of heavy ions created microscopic analogs of Big Bangs, extremely dense fireballs with monstrous temperature readings. Under such extreme temperatures, atomic nuclei underwent melting, forming a unique state of matter known as quark-gluon plasma. Thus, in controlled laboratory conditions, plasma with the highest temperature ever recorded was obtained. And although 10 trillion degrees is an incredibly high temperature, it is apparently not the ultimate limit, as the current level of modern technology does not yet allow for a further step in this direction. To begin the search for the hottest sources in the universe, it is advisable to start by studying the cosmic objects closest to us. The planet Venus is distinguished by an abnormally dense atmosphere with a pressure equivalent to 90 Earth atmospheres. Thanks to a powerful greenhouse effect, the surface temperature of this planet reaches 480 degrees Celsius, exceeding the temperature indicators on Mercury. Some cosmic objects, for example, the asteroid Phaethon, have the ability to approach the Sun at a record short distance. Its temperature at the perihelion of its orbit can reach 750 degrees Celsius. An even higher temperature is observed on the moon Io, which became one of the biggest surprises for scientists when exploring the Jupiter system with space probes. Its surface is the youngest in the solar system, completely devoid of impact craters. Measurements taken by the Galileo probe demonstrated that the temperature of volcanoes on this moon reaches at least 1,340 degrees Celsius. Our Sun's surface has a temperature of about 5,500 degrees Celsius. However, at a distance of approximately 10,000 kilometers from the star's surface lies the solar corona, which we perceive as a kind of halo. Its temperature already reaches 1 million degrees. The temperature of a solar flare can be many tens of millions of degrees. In the universe, the Sun is an ordinary star. The surface temperature of ordinary stars varies from 2,000 degrees Celsius for red dwarfs to 30,000 degrees Celsius for blue dwarfs. There is a special class of stars called Wolf-Rayet stars, whose surface temperature can exceed 50,000 degrees Celsius. The number of known stars of this type in the local group of galaxies can reach several thousand. Such stars are characterized by high density and the presence of ejected envelopes resembling planetary nebulae. They are believed to represent the final stage of the evolution of single massive stars before the supernova explosion stage. The hottest star among them is WR102, with a temperature of 210,000 degrees Celsius and a luminosity 500,000 times that of the Sun. The mass of this star is estimated at 20 solar masses with a radius less than 0.4 solar radii. Stellar remnants exhibit even higher temperature readings. In 2015, the discovery of the hottest white dwarf, designated RX J0439-A6809, was announced, with a surface temperature reaching 240,000 degrees Celsius. Even higher surface temperatures are characteristic of exotic stellar remnants, neutron stars. Their maximum radiation falls in the X-ray range and gamma rays. The brightest sources of gamma rays are three neutron stars: the pulsar in the Crab Nebula, the pulsar in the Vela Nebula, and the radio-quiet Geminga star. It is believed that at the moment of a neutron star's formation, its surface temperature is about 100 billion degrees Celsius. This colossal temperature, though astonishing, is far from the absolute limit. Stellar mass black holes, such as Cygnus X1, are known to be powerful sources of X-ray radiation visible in our planet's sky. Recent scientific observations have revealed that the effective temperature of the central region of the nearest quasar, 3C273, reaches 40 trillion degrees. Moreover, there is a hypothesis that the effective temperature of dark matter in active galactic nuclei can be on the order of 10 to the 21st power Kelvin, which is equivalent to zeta electron volts. This value is tens of millions of times higher than the temperature of visible matter recorded in these objects. It is quite probable that the universe hides even hotter bodies from us, which remain inaccessible to our study for now. It is hypothesized that the highest temperatures were reached at the moment of the so-called Big Bang, or at the dawn of the inflationary stage of the universe's development. Theoretical calculations indicate that the temperature of our universe then corresponded to the Planck temperature. Modern physical science considers this point to be an absolute maximum, significantly exceeding 10 trillion degrees. According to a new theory, the limiting temperature should be equal to 142 quintillion. This number significantly exceeds the values obtained in terrestrial experimental studies. This difference is explained by the fact that for the state in which the experimental system was, a strict definition of the concept of temperature is inapplicable. Temperature, in its classical sense, is defined for a state of thermodynamic equilibrium, in which the so-called Maxwell-Boltzmann distribution of particle velocities is observed. This is a probabilistic distribution of fundamental importance for the kinetic theory of gases, which, in turn, explains numerous properties of gases, including their pressure and diffusion. However, this distribution was not taken into account in the experiment mentioned. Based on the foregoing, it can be concluded that, theoretically, an absolute maximum temperature most likely does not exist, since any system can be heated to arbitrarily high temperatures. The main question is what processes will occur at such extreme temperatures, and whether we will be able to adequately describe them. At extremely high temperatures, molecules will first begin to break down into atoms, then atoms into nuclei and electrons, nuclei into nucleons, and nucleons, in turn, into quark-gluon plasma, consisting of quarks, which are fundamental particles that make up protons and neutrons. What happens next remains unclear, since quarks are considered elementary particles and have nothing left to break down into. What the consequences will be at even higher temperatures, pressures, and superspeeds is completely unknown. Thus, the maximum temperature limit is directly related to our current lack of knowledge about the behavior of matter under extreme conditions. The question, apparently, remains open for further research. The idea that the stars visible in the night sky Our distant worlds and systems analogous to our solar system inevitably led to speculation about the possibility of planets around them, and consequently, the existence of life on these celestial bodies. However, detecting such planets is extremely difficult because they have significantly less mass compared to stars and emit much less light. Despite numerous attempts, true success only came at the end of the 20th century. By the late 80s, several observation methods had reached the required precision, and in the early 90s, a period of active exoplanet discoveries began. Currently, several thousand such planets are known, and their number is steadily increasing. It has become clear that other planetary systems and their components can differ significantly from what we observe in our own system. A vast cosmic abyss filled with exoplanets has opened before us, and now we must understand how these objects are structured, how they formed, and how they will evolve in the future. Let's consider one of the most famous exoplanets, HD 24b, also known as Osiris or the evaporating planet. Osiris, or HD 29458b, is located in the constellation Pegasus at a distance of 153 light-years from our Sun. Typologically, it is a hot Jupiter, a gas giant planet whose mass is close to Jupiter's, but which is located significantly closer to its star than Jupiter is to the Sun. The radius of Osiris is approximately 100,000 kilometers, which is equivalent to 1.3 times Jupiter's radius. Its mass is estimated at 0.69 Jupiter masses. The distance to its star is only 0.047 astronomical units, which is significantly less than the distance from the Sun to Mercury. A year on this planet lasts only 3 Earth days. The discovery of this planet's atmosphere was made possible because HD 29458b was the first planet for which its own emission spectrum, separated from the star's overall radiation, could be obtained. Characteristic sodium absorption lines were found in this spectrum. Subsequent studies allowed for hypotheses about the extent, internal structure, and temperature of its atmosphere, which is believed to begin at a distance of 3.1 Jupiter radii from the planet's center. Osiris is a colossal gas giant filled with various gases, including hydrogen, oxygen, carbon, carbon dioxide, methane, and water vapor. At first glance, this planet's atmosphere should be quite stable. Current estimates suggest that the temperature of the lower atmospheric layers reaches 1,300 Kelvin, which, seemingly, should not allow molecules and atoms to overcome gravity and escape into space. However, it is well known that temperature can vary significantly with increasing altitude. The reason for the high temperature of the uppermost atmospheric layers is intense heating by short-wavelength ultraviolet radiation from the star. For Osiris, which is significantly closer to its star than Earth is to the Sun, heating by far ultraviolet radiation occurs with much greater intensity. Recent additional observations of the planet in the ultraviolet range, performed with the Hubble Space Telescope, demonstrated that in the Lyman alpha line, Osiris eclipses its star much more noticeably. The star's brightness decreases by 15%, which corresponds to the size of the hydrogen cloud surrounding the planet, with a diameter of approximately 4.3 Jupiter radii. Since the size of the Roche lobe, i.e., the zone within which matter is held by the planet's gravity, for Osiris is 3.6 Jupiter radii, the results of these observations can only be explained by the assumption that the planet is continuously losing matter at a speed of about 130 kilometers per second. This speed significantly exceeds the escape velocity from Osiris's surface. According to current estimates, the planet Osiris loses between 100 and 800 tons of hydrogen per second. This means that over a period of approximately 5 billion years, the planet could have lost up to 7% of its total mass. However, there is a possibility that hydrogen loss could be mitigated by the exoplanet's magnetosphere if it is still actively functioning. It is possible that Osiris's atmosphere is typical for planets orbiting Sun-like stars at a distance less than 1/10 of an astronomical unit. But unlike others, Osiris is evaporating at an incredible rate. Today, this exoplanet is more like a giant comet planet, forming an extensive tail of various gas streams. At its current evaporation rate, it will be completely destroyed in 1 trillion years. Researchers have successfully modeled a super-powerful storm raging on the planet Osiris. This global tornado arises because the side of the planet that never faces the star is significantly colder, and this enormous temperature difference generates extremely strong winds. To create a more accurate model, astrophysicists took into account many factors determining the complex interaction between the stellar wind and the planet's atmosphere. These factors included charge exchange between the stellar wind and neutral atmospheric particles, their ionization, gravitational effects, pressure, radiative acceleration, and spectral line broadening. These detailed calculations helped establish that winds of carbon monoxide rage on Osiris, with speeds of approximately 2 kilometers per second or 7,000 kilometers per hour, with possible variations from 5,000 to 10,000 kilometers per hour. This scorching and rapidly evaporating exoplanet was first discovered in 1999 using the Doppler method. At that point, just over 30 planets had been found this way. However, many astronomers were hesitant to share their colleagues' enthusiasm until another group of astronomers managed to find the same planet using the transit method, which definitively confirmed the existence of new worlds. Since then, significantly more advanced tools for deep space exploration have emerged. A significant breakthrough in this and many other areas of astronomy is expected with the upcoming launch of the James Webb Space Telescope. While not exclusively designed for exoplanet discovery, its technical capabilities will be sufficient for substantial advancements in the general search for exoplanets, and in particular, Earth-like planets. Also worth mentioning are the future largest telescopes currently under development and construction: the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope. These powerful instruments will undoubtedly enable the discovery of many new exoplanets, and more importantly, they will expand the lower limit of their detection. This will allow for finding many more Earth-type planets and planets significantly smaller than ours, even to the point of potentially detecting moons around exoplanets. Our cosmic home, in essence, is a universe teeming with exoplanets. The number of confirmed celestial bodies discovered beyond our solar system has already reached thousands, and this number is steadily increasing. In the coming decades, it will likely grow to tens of thousands as observational power and the number of automated telescopes launched into space are constantly expanding. By precisely measuring the sizes and masses of these distant worlds, scientists can determine their chemical composition, from extremely rocky ones, similar to Earth and Venus, to gas giants resembling Jupiter and Saturn. Exoplanets are formed from the same chemical elements as the planets in our solar system, yet their internal structure can differ significantly. Some of them may be dominated by water or ice, while others may be rich in iron and carbon. Among the identified worlds are lava planets, completely covered in molten seas, huge celestial bodies with a density comparable to styrofoam, and, conversely, dense planetary cores that continue their rotation around parent stars. Some of the latest discoveries represent truly captivating and, at times, extreme cosmic objects. One such striking world was discovered in the system of the star HD 83443. The new exoplanet, designated HD 8344b, has a mass 1.5 times that of Jupiter and is characterized by endless storms and hurricanes. Its orbit has a semi-major axis of 0.08 astronomical units and an eccentricity of 0.76. A year on this planet lasts 22 Earth years, making it anomalously cold for its size. The system contains 2 exogiants moving in completely different orbits. The most probable explanation for such a configuration is gravitational scattering that occurred in the past, which made HD 83443b a short-period planet and brought HD 83443c into its current wide orbit. It is possible that a third exoplanet previously existed in the system and was ejected from it as a result of these dynamic processes. The climate of the next exoplanet, 55 Cancri E, is a veritable hellish resort. This planet orbits so close to its sun-like star that its surface is engulfed in fire. The temperature there reaches 2,436 degrees Celsius. This exoplanet is located 50 light-years from Earth and belongs to the class of super-Earths, planets whose mass is several times that of Earth. The surface of this scorching world is covered in lava and continuously ablaze. 1 year on, it lasts only 18 hours. Gravitational forces keep one hemisphere of the planet in perpetual light and the other in endless darkness. Significant surface temperature fluctuations are attributed to possible volcanic activity, which spews huge clouds of dust into the atmosphere, covering the planet and blocking thermal emissions. If the Webb telescope detects an atmosphere on this burning world where oxygen or nitrogen predominates, then images will reveal the lava-shrouded surface of the super-Earth 55 Cancri E. The next object is Gliese 167cc. This is one of 3 exoplanets that orbit an M-type red dwarf. The star is located 22 light-years from Earth in the constellation Scorpius. The planet completes one orbit around its star every 28 Earth days. The discovered exoplanet is located in the habitable zone of its star and is likely an ocean planet. With a high degree of probability, storms and other phenomena related to a large volume of liquid medium and strong winds may rage on it. The existence of life on this planet is also possible, although it would be radically different from Earth's. Gliese 667 cc is a super-Earth with a mass 3.7 times that of Earth, so gravity there will be significantly higher. If we assume that the planet has an atmosphere similar to Earth's, then the surface temperature would be around 30 degrees Celsius. However, if its atmosphere turns out to be much denser than Earth's, then it could be similar to Venus, and conditions would be significantly less comfortable. Due to the exoplanet's close proximity to its star, it is quite possible that it is tidally locked, meaning eternal day on one side and eternal night on the other. The star in the sky of Gliese 667 cc appears much larger compared to our Sun, probably as a red disk, 3 times wider and 10 times larger in area. The fourth planet is TIC 172998b, orbiting 2 stars. It was discovered thanks to the TESS space telescope. To date, only 14 such circumbinary exoplanets have been discovered as they orbit binary stars. This new world is a gas giant the size of Jupiter, but much more massive, 2.96 Jupiter masses. It orbits with a period of 200 days around 2 sun-like stars, which, in turn, orbit each other. High-resolution images in the near-infrared part of the light spectrum revealed a signal indicating the possible presence of a moon in the planet's orbit, probably twice the size of Earth. Although moons are ubiquitous in the solar system, none have yet been confirmed outside it. It is believed that the environment of cold gas giants, distant from their stars at a distance similar to the orbits of Jupiter and Saturn, is a preferred place for their formation. The conditions on this moon are currently unknown. Moving on to Kepler 1649c, which is located 300 light-years from Earth and is only 1.6 times larger than it. This is a rocky world located within the habitable zone. The planet is close to its star. A year on it lasts about 19 Earth days. It is currently known that the planet receives 75% of the star's light relative to Earth. Its equilibrium surface temperature is estimated at minus 39 degrees Celsius. On this planet, there's a high probability of liquid water seas and oceans. To date, no flares have been observed on the star Kepler 1649, which is extremely important because it is a red dwarf, known for its unstable activity. In the same system, there is at least one more rocky planet of similar size, but its orbit is almost twice as close to the star. The next amazing world is GJ 1132b, located approximately 40 light-years from the Sun. The planet is 1.8 times larger than Earth, and it completes a full annual orbit in just 1.6 Earth days. An atmosphere has been detected on this exoplanet. This circumstance is of particular interest, as the planet is extremely close to its star and, according to all calculations, should have long since lost it. The planet may have volcanic activity, as it contains an abnormally high amount of hydrogen cyanide, reaching 0.5%. It is also rich in hydrogen cyanide, methane, and ammonia. In some ways, the planet is similar to Earth. It has similar density, size, and age. Both planets started with atmospheres dominated by hydrogen, and both were hot before cooling down. However, the history of planet formation differs greatly. This example shows that not all terrestrial planets begin and end their journey like Earth. Some of them may form as mini-Neptunes and then become Earth-like due to mechanisms by which the star evaporates the original atmosphere. And finally, the seventh and most distant world is M51 ULS-1b. This is one of the first officially confirmed planet status objects found outside our Milky Way galaxy. The exoplanet was discovered in the Whirlpool Galaxy, or M51, located 28 million light-years away. The exoplanet is in a binary system, orbiting two large objects that revolve around a common center of gravity along with a massive companion star. The transit observed by astronomers lasted about 3 hours. During its course, the detected X-ray emission from the star dropped to 0. This helped researchers calculate that the object could be about the size of Saturn and orbits a neutron star or black hole at a distance twice that of Saturn from our Sun. However, this distant exoplanet will not pass in front of its star again for another 70 years. Therefore, it will be a long time before astronomers can observe this event again. The preceding discussion presented only a few of the countless fascinating worlds, but humanity's capabilities for studying them are rapidly expanding. Modern and future telescopes, such as the already operational James Webb, as well as those planned for launch or commencement of operations in the coming decades, including the Cheops telescope, which will begin operations in 2023, the Plato Space Telescope, expected in 2026, the Giant Magellan Telescope, or GMT, in 2029, the Extremely Large Telescope, or ELT, in 2027, and the Roman Space Telescope, also in 2027, will significantly augment our research capabilities. With their help, it will be possible to precisely measure the atmospheres of small exoplanets, obtain direct images of them, decipher microlensing signals to detect even smaller planets, work with more subtle radial velocities, and collect significantly more extensive statistical data. And, most importantly, we can anticipate nearing the discovery of the so-called Earth 2.0, as well as adding even stranger and more unexpected cosmic objects to the exoplanet collection. All these grandiose efforts are undertaken for the advancement of science and the search for an answer to one of the most fundamental questions of existence. Are we alone in the universe? Studying the diverse spectrum of exoplanets and planetary systems discovered to date, from tiny to giant, from Earth-like to utterly bizarre, not only helps us understand the mechanisms of formation and evolution of these specific systems, but also provides invaluable clues to understanding whether life can exist anywhere else in the boundless expanse of space. In the bottomless night sky, countless stars shine in all directions from our planet. The closest star system to us is the famous Alpha Centauri. However, for Alpha Centauri itself, our Sun is not the closest extrasolar star. At a distance of 3.7 light-years from Alpha Centauri in the constellation Vela lies another binary star system consisting of two brown dwarfs, Lumen 16a and Lumen 16b. This unique star system, scientifically designated WISE J Tandro 4955 319R061, was discovered using the WISE telescope, which operates in the infrared range. The discovered pair of substars has taken the honored title of the third closest star system to the Sun, surpassed only by the triple Alpha Centauri system, located at a distance of 4.3 light-years, and the solitary wandering Barnard star, 5.9 light-years away from us. The distance from our Sun to the brown dwarf pair, Lumen 16, is 6.5 light-years. Both stars in this binary system are brown dwarfs, meaning they possess intermediate physical characteristics between ordinary planets and full-fledged stars. Their mass proved too small to achieve sufficient temperature and pressure to initiate hydrogen fusion in their cores, the process that powers true stars. As a result, they remain extremely cold and dim, resembling giant planets like Jupiter more than bright luminaries like our Sun. Due to their nature, brown dwarfs do not emit their own light in the visible range and are therefore extremely difficult to observe directly. Nevertheless, thanks to their relatively close proximity to the Sun, it is possible to conduct precise astronomical studies using both ground-based and orbital telescopes. The mass of the brown dwarf Lumen 16A is estimated to be between 40 and 50 Jupiter masses, while Lumen 16B's mass ranges from 30 to 50 Jupiter masses. These two substars orbit a common center of mass at a distance exceeding 3 astronomical units, which is approximately 500 million kilometers, completing a full orbit in 25 years. They are slowly approaching each other as their rotating masses emit gravitational waves, which gradually leads to a decrease in their orbits. Given enough time, they will inevitably collide, and such a collision is very likely to result in the emergence of a completely new star. However, the scenario of spiraling into each other due to gravitational waves for such well-separated brown dwarfs would take an extremely long time, beyond human comprehension. Collisions of brown dwarfs, though rare, are quite probable on cosmic scales and can give rise to a new star, such as a red dwarf. By the time of such a hypothetical event, the brown dwarfs would likely have exhausted all their internal energy and cooled to a surface temperature of only a few degrees above absolute zero. But the energy of the collision or merger must be sufficient to create such extreme pressures and heat in the core that if the critical mass threshold of approximately 76 Jupiter masses is overcome, nuclear fusion can begin. Such a newborn star would have a small mass, be red in color, and live for an exceptionally long time, over 10 trillion years, significantly exceeding the current age of the universe. However, the distance between the brown dwarf's Lumen 16A and Lumen 16B will decrease very, very slowly. According to calculations, this process will last longer than the lifetime of any existing star, galaxy, or even the central black hole in a galaxy. Such an incredible duration is due to the small mass of both objects and the significant distance between them. Most likely, these substars will become true stars faster if they collide on their path with another failed star, such as a rogue brown dwarf or a massive planet. It has also been discovered that brown dwarfs can emit flares similar to ordinary stars, demonstrating unexpected activity. However, for the Lumen 16 system, the friction effect exerted by one brown dwarf on the other, which could gradually pull them together, will not work due to the too great distance between them. Such an effect would be possible if the distance between the dwarfs was comparable, for example, to the distance from the Sun to Mercury. Nevertheless, this circumstance does not prevent scientists from continuing to learn new facts about this amazing system and expanding our knowledge of the diversity of cosmic objects. Observational data and images obtained through the VLT telescope's instruments allowed scientists to create the world's first surface map of a brown dwarf, as well as to determine an approximate weather forecast for it. Thanks to the close proximity of this system to Earth, astronomers were able to thoroughly assess the dwarf's topography and the structure of its upper atmospheric layers by analyzing distortions in the star's spectrum at various points on its surface. As a result of these studies, an approximate map of Lumen 16b was created and a weather forecast was developed, the quality of which is comparable to the results of early artificial satellites. The surface map of Lumen 16b appears to be formed of vast contrasting light and dark areas, which have been named clouds. Observing these atmospheric formations over several hours confirmed Lumen 16b's 5-hour rotation period, with carbon dioxide and water absorption zones predominating in these regions. The predicted rotation speeds of the Lumen 16a and Lumen 16b components were estimated at approximately 17 kilometers per second and 26 kilometers per second, respectively. This means that the rotation axis of component B must be inclined to the plane of the sky at an angle of less than 30 degrees, assuming its radius is approximately 1 Jupiter radius. It remains an open question how similar brown dwarfs like Lumen 16a and Lumen 16b are to Jupiter, which has regular belts and zones formed by large parallel longitudinal jets, or whether they are dominated by a constantly changing pattern of giant storms or vortices, similar to those observed at Jupiter's poles. Furthermore, it has been revealed that the Lumen 16 star system consists exclusively of two objects, two dwarfs. There are no planets or planet-like bodies whatsoever. However, something is causing lumen 16a to wobble. There are three possible explanations for this phenomenon: an inaccuracy in the binary system's orbital solution, an inaccuracy in the proper motion estimate, or the presence of an as-yet undetected companion around this component that is causing these oscillations. In any case, it would be a small, cold planet where everything has long since frozen. Currently, the available data does not allow for either confirmation or refutation of a planetary signature, and astronomers emphasize the urgent need for a more precise determination of these brown dwarfs' orbits. The Lumen 16 system continues to be intensively studied, as its unique characteristics provide a new perspective for understanding the nature of brown dwarfs. Its relatively small distance from Earth and binary nature represent an ideal proving ground for research and a better understanding of the characteristics of similar objects in the universe. Discoveries made during the study of the Lumen 16 system could have far-reaching implications for our understanding of stellar evolution and brown dwarf-type stars in general. The James Webb Space Telescope is currently actively collecting data on exoplanet K2-18b, which is approximately twice the size of Earth and is located in a system 120 light-years away from us in the constellation Leo. The planet draws particular attention because biosignatures have been detected in its atmosphere. On Earth, these complex compounds are produced primarily by phytoplankton in marine environments. Therefore, the detection of such organic matter in the atmosphere of a distant planet has generated immense interest and suggests that K2-18b may not only harbor marine life, but also be completely covered by an ocean, which, in turn, due to the closest star, generates colossal tsunamis. Let's consider how ocean planets are born in distant star systems. Ocean planets are a special type of planet consisting primarily of ice, rocky materials, and metals. Depending on their distance from their parent star, they can be entirely covered by an ocean of liquid water up to 100 kilometers deep. The precise value of this depth directly depends on the planet's radius. At greater depths, the pressure becomes so significant that water can no longer exist in a liquid state and solidifies, forming various modifications of ice. If, during the formation of a planetary system originating at a significant distance from its star, a protoplanet reaches a mass of approximately 10 Earth masses, it becomes massive enough to attract hydrogen and helium, transforming into a gas giant. A planet of slightly smaller mass, approximately 6 to 8 Earth masses, which has not reached the threshold of 10 Earth masses, turns out to be composed primarily of ice and rocks, similar to the moons of gas giants in our solar system. So, if a celestial body has enough mass to independently orbit its star and not be engulfed by the gravitational field of a neighboring gas giant, but is not massive enough to attract hydrogen and helium from the surrounding gas and dust cloud where it is forming, then within a simplified cosmological model, we are presented with an ice planet. Such an object is approximately half ice and half solid rock, which of course makes it an extremely cold and lifeless world. However, over time, during its migration through cosmic space, powerful turbulent perturbations arising in the protoplanetary gas and dust disk can significantly alter the planet's orbit. As a result of such transformations, this ice planet may approach its star close enough for its outer ice shell to melt, and then its entire surface will be completely covered by a boundless ocean of liquid water, whose depth can vary from 70 to 140 kilometers. At the same time, the pressure at the bottom of such an ocean, reaching approximately 15,000 atmospheres, will be sufficient to form special polymorphic modifications of ice. These forms of ice are heavier than liquid water and, under such colossal pressure, will never melt. Below this layer will extend a solid crust consisting of various ice modifications about 5,000 kilometers thick. And finally, at the very center of the planet will be a solid core with a radius of approximately 8,000 kilometers, formed primarily by a rocky mantle and metallic elements. Ocean planets, as is known, are extremely rare in cosmic space. Nevertheless, such a unique world was discovered thanks to observations by the James Webb Space Telescope. This exoplanet completes a full orbit around its star, named K2-18, in 33 Earth days and receives 5% more light energy from it than Earth does from the Sun. Previously, this planet was thought to belong to the class of gas dwarfs, also known as mini-Neptunes. These celestial bodies are something between solid planets, like Earth, and gas giants, like Uranus and Neptune. However, the results of the latest research convincingly indicate that planet K2-18b is a Hycean. Hyceans are planets whose surface is completely covered by water. It is assumed that moderate temperature regimes and conditions quite favorable for the emergence and maintenance of life are supported on their surfaces. The exact chemical composition of this planet's atmosphere is still under active study, but it has already been reliably established that it contains hydrogen, helium, carbon dioxide, and methane, a composition very reminiscent of early Earth's atmosphere. Thus, the discovered exoplanet can rightly be called a water world. Of particular interest is the possible detection of traces of dimethyl sulfide, or DMS. Researchers could not directly identify this organic compound, but recorded convincing signs of its presence. This in itself is a very significant and intriguing discovery. On our planet, Earth, this organic substance is produced exclusively by bacteria, as well as plankton living in water and some types of algae. Under normal conditions, it is produced by bacteria in wastewater and sewage systems, which is the cause of its characteristic unpleasant odor. However, in extremely small concentrations, this same substance can give marine air a refreshing and invigorating aroma. The star system hosting this remarkable ocean planet includes a star significantly different from our Sun. It is a red dwarf, a celestial body that is dimmer and significantly cooler than our star. Nevertheless, it reliably provides its planet with heat and light. The planet receives enough light and heat. Moreover, it receives no less than Earth, as it is located in the so-called habitable zone. However, since we are talking about a red dwarf, the situation here is not so straightforward. Red dwarfs are the smallest, most common, and longest-lived stars in our galaxy. Superflares, which are powerful energy outbursts, are more often observed in younger and more active red dwarfs, and their intensity can be thousands of times stronger than in similar, but older, stars. The emissions recorded on the star K2-18 were significantly more powerful than any ever observed on the Sun, and they are highly likely to have a substantial impact on the planet's potential habitability. Such flares indeed have the ability to strip away planetary atmospheres, but this does not necessarily mean inevitable doom for unknown forms of life. Furthermore, processes capable of replenishing its atmosphere may be actively occurring on the exoplanet. This is undoubtedly a harsh and unfriendly environment, but at present, astronomers are not yet ready to make a categorical statement about its complete sterility. Among other things, the strongest flares also affect the tidal forces and internal activity of the ocean planet's interior. This means that in an instant, huge masses of water can be set in motion, generating waves of gigantic proportions. How big can they be? First and foremost, it is worth understanding how a tsunami fundamentally differs from small waves observed on the seashore. The difference between these two types of waves lies not only in their size and height. The most important difference between a tsunami and ordinary waves is the mechanism of their origin. Ordinary waves arise from the action of wind. They are rarely as destructive as tsunamis, although they can cause damage to coastal infrastructure. As a rule, damage in such cases is limited to a few meters from the shore. A tsunami, on the other hand, originates not near the coastline, but, as a rule, at a significant distance from it. Several key factors contribute to the generation of these giant waves, known as tsunamis. Among them are submarine earthquakes, powerful volcanic eruptions, and significant submarine or coastal landslides. Although the latter relatively rarely generate tsunamis of destructive force, it is noteworthy that one such landslide caused the most colossal tsunami ever recorded in human history. Approximately 85% of all tsunamis are the result of submarine earthquakes. The highest tsunami ever recorded reached a peak height of over 460 meters and traveled at a speed of about 160 kilometers per hour. This extraordinary event occurred on July 9, 1958, in Alaska. A massive landslide descending from mountains approximately 1 kilometer high was triggered by an earthquake and dumped millions of cubic meters of rocks and ice into the water. These masses generated a wave of such incredible power. Surprisingly, water, at first glance, seems soft and completely safe. The volume of seawater contained in a 1 meter by 1 meter cube weighs about 1 ton. When a tsunami crashes hundreds of millions of tons of water onto a coastline, moving at speeds exceeding 100 kilometers per hour, such a wave can become deadly upon first contact. Such destructive scenarios make one seriously consider that the planet K2-18b may well turn out to be a merciless and harsh world. Nevertheless, K2-18b exhibits an adequate carbon content, while the amount of minerals and other elements of the Earth's crust, which typically dissolve in ocean waters and thereby remove carbon from the atmospheric layer, is relatively small. For such planets, which already possess a sufficient water reservoir, the key becomes maintaining a stable carbon cycle between the atmosphere and the ocean. With the correct concentrations, this process proves entirely sufficient to ensure long-term stability of conditions. Initial modeling results suggested that stars similar to our Sun were necessary for these processes. However, the latest data show promising prospects for planets orbiting red dwarf stars as well. Planetary systems around red dwarfs are now considered extremely promising candidates for the origin and evolution of life. This is because such stars are, in a sense, significantly brighter than our Sun, as they provide potential support for life over much longer time intervals. According to leading researchers, these favorable conditions may well extend to planets located in red dwarf systems, which include K2-18b. Theoretically, only constant radiation from their parent star would be sufficient to sustain life on such worlds. To achieve greater clarity and confirm the data obtained, further, more detailed and in-depth astronomical observations are required. This important work is currently being actively pursued by the James Webb Space Telescope. It uses its highly sensitive infrared sensors, which allow for additional spectral analysis. The purpose of such analysis is to detect other potential biosignatures and definitively confirm the presence of organic compounds. To date, this represents the only practically feasible method for searching for signs of extraterrestrial life in other planetary systems. And who knows, perhaps beneath the massive layer of water on this planet truly lies a vast, as yet unexplored, aquatic world. A team of researchers actively working with the James Webb Space Telescope has announced the identification of the most compelling evidence to date for the potential existence of life beyond our solar system. According to their presented data, certain chemical compounds have been discovered in the gaseous envelope of exoplanet K2-18b that, on Earth, are produced exclusively by living organisms. Specifically, these are two gaseous substances, dimethyl sulfide, or DMS, and dimethyl disulfide. In terrestrial conditions, these gases are primarily released by microscopic marine algae and phytoplankton. Scientists hypothesize that such a discovery may indirectly indicate the presence of microbial life on this distant planet. However, at this stage, it is still too early to speak of the discovery of advanced alien civilizations. For now, it is merely a possible biosignature, meaning signs of biological activity, which in itself is an incredibly significant and astonishing discovery for all of humanity. In any case, additional, more thorough observations are required to form definitive and irrefutable conclusions. Nevertheless, this momentous discovery is quite capable of becoming a key turning point, bringing us significantly closer to answering one of the oldest and deepest questions that has troubled humanity for centuries. Are we alone in the vast universe? One thing is absolutely clear. Today we have a much greater amount of information about planet K2-18b than ever before. This data concerns its atmospheric composition, surrounding climatic conditions, the influence of the nearest star, and even the hypothetical surface of this amazing celestial body.